Okay, guys, let me just make a little note here because I'm going to have to make a small change. It's in your favor, but regarding the grading of the class, I don't know what I was thinking, but with the quizzes, the quizzes that y'all took last time, I'm going to count those as 50 points each, all right? So you just multiply your score times 5, right? And that'll give you your score, or just take it as a percentage. And I will guarantee you at least 6 quizzes. But in practice, I usually get at least 7 and maybe even 8. And then I'll drop those lowest 3 grades. You follow what I'm saying? So you get like at least 7 or at least 6, so you at least get 1 drop grade. But I'm almost certain we'll get 7 quizzes. I try to do them fairly frequently. Like we'll probably have, what's today? Thursday. We'll definitely have one next week. I'll let you know over email. Um, and so I count your 5 highest quizzes. We drop probably to maybe even 3. Definitely 1, probably 2, maybe 3 of your lowest quizzes. As a result, I don't do makeups for the quizzes. So if you miss one, you just count that as one of your almost certainly 2 drop quizzes. Okay? Y'all clear on that? All right. I'll redo the syllabus. It's gonna it benefits you in the long run because you get those drop quizzes. You get more drop quizzes. All right. Um, y'all doing okay this morning? Yeah. The grades on the quiz were pretty good all overall. There were a couple perfect scores, several 9s, some 8s. It was good. All right. So let's do this example. You're not going to have to do a calculation like this, but I do want you to understand how the torque is affected. Remember, there are a couple of things that the torque can be affected by, like going back to the door. Your torque can be affected just by the magnitude of the force. Like if I just push a little bit, I get very little torque. But if I push a lot, I get a big torque. It can also be affected by the length of the moment arm. That's what we call R. You can call it the lever arm as well. So for example, if I push here, I get very little torque. That's why we never open the door pushing at the hinge. In fact, if I push at the hinge, I get zero torque at all because R is equal to 0 at that point. And then a third way that we can affect the torque is what? Do y'all recall? We did this with the rulers and the weights. The length of the moment arm, the amount of force that you apply, and then also the angle. Right, who said that? Mariah? Mariah, right? Yeah, so the angle. So if you apply the force at a shallow angle, like right here, I'm applying the force at 90 degrees. That gives me maximum torque. But if I apply it at an angle like this, then I don't get as much torque. In fact, it's kind of hard to open the door like this because I'm just not getting much torque from the force that I'm applying. I'm applying the same force as I do here, but I'm not able to move the door because that angle is very small. And so this comes up, we mentioned this last time with the deltoids, that the deltoids, these muscles, they sort of, where do they run? Do they connect up here in your shoulder and then come down to here? Is this your deltoid? All right, athletic trainer. This thing right here. Yeah, so it has a very shallow angle. I think your insertion point is right about here. Yeah, so it has a pretty shallow angle, right? That if I were to draw it as a diagram, I'll sort of draw it like this guy. This deltoid applies a force that's at a really shallow angle right there. And so that force, even though it applies a really big force, doesn't apply very much torque to your arm. And that's why, you see those big guys over in the rec center doing these things and they're holding like little, 10, 20-pound dumbbells because it's very hard to lift those because of that angle is very shallow and you get very little torque. All right, so let's just sort of do a quick assumption for, let's draw our arm. Our arm is right here. It rotates, at the shoulder joint, which is what type of joint? Ball and socket, right? Remember, it's not a true ball and socket because it's, there's no true socket. It just sort of goes up next to it, but we still call it a ball and socket. Our forces, we have a couple of forces. We have our force due to the muscle or the deltoid. I'll call that F sub D. And, we'll call that about 10 centimeters or so. It's about 10 centimeters. So that distance from here to here is about 10 centimeters. And then this angle is very shallow. I don't know, maybe 5 degrees or so. It's very small. Um, and then we want to think about the weight of the arm and then also the weight of the dumbbell. Now here we have a 10-pound dumbbell. Let's see, kilogram is about, what, 1.5 pounds? Is that right? Yeah, so 10 pounds is 6 or so kilograms, 7 kilograms. I'll say that it's 5 kilograms to make our math a little easier. And now, what is the weight of the arm in pounds? Do you guys have any idea what the weight of the arm is? Kai, Kai? Yes. What is the weight of the arm? We just ask, like, what do you think in pounds? Maybe 10, 20 pounds? What do you, 20? 10? I guess it depends. Like, if you're Arnold Schwarzenegger, your arm's going to be a lot heavier than that. But we'll say 20, okay? So 20 pounds, we'll say 10 kilograms, okay? Is that too heavy for an arm? You think? Oh, come on. All right, well, look, I'm going to put 10 kilograms. I don't even care what you think, frankly. I'm just going to put 10 kilograms. All right, and so let's see, my arm, I do care what you think. You know, that's not true. My arm's about 70 centimeters long, so we'll say that this distance is 30 centimeters. That's the distance to the midpoint. So this is my arm. We're going to talk about the center of mass. The center of mass of my arm. Seriously? The center of mass of my arm is it at the midpoint? Is it to the right of the midpoint, or is it to the left of the midpoint? Morning. What do y'all think? The center of mass, you might not know this right off. We're going to talk about it in just a bit. But the center of mass, is it at the midpoint of my arm? Right in the, if it's 70 centimeters long, is it at 35 centimeters? Is it to the left or to the right of the midpoint? Well, your arm's not homogeneous, right? Yeah, so you want to think about what's the biggest part of your arm. Right, because this part of your arm, you have more muscle mass and this with your bicep and your tricep. So yeah, so I have it here so that the center of mass of my arm, we're going to get to that soon, is just to the left of the midpoint. So if this is 70 centimeters long, I have it at about 30 centimeters. And then the dumbbell, we'll say, is at the very end, so it's going to be 70 centimeters. So now we want to figure out what is F of the deltoid in order to make this thing balance. You're not going to have to deal with trig functions at all in your on your test, but I just want to show you how this works out. It does similar to what we've done before, is it will set the torques going in one direction equal to the torques going in the other direction. We did this last time. So I have the force of the deltoid. This is causing the motion to go, what's that, counterclockwise. And then these two forces are causing the arm to go clockwise, right? I have the weight causes it go down that direction, but the deltoid makes it go up in that direction. So I'm going to take those two sets of torques, counterclockwise and clockwise, and set them equal to one another because they have to be equal if it's a static situation, meaning it's not moving. I have to have equal but opposite torques. All right? So the counterclockwise, remember torque, I gave you this expression, is FR. That's what we've been using, and that's what you'll need to use for your exam. But also, there's this sine theta term. You'll need to know qualitatively what that means and what that does. If you have a shallow angle, I get less of a torque. All right, so torque is, the torque on this side is going to be force of the deltoid times the distance, which is 10 centimeters. That's 0.10 meters. Move that decimal place over 2 spots to the left. 10 centimeters is less than a meter. In fact, it's 1/10 of a meter. And then this sine of the angle theta, this is actually, or this is going to be sine of 5 degrees, has to equal to 10, excuse me, this force this force right here, the weight, is going to be 100 newtons. Remember our weight, Fw, is equal to the mass times g. You need to understand that mass and weight are two different things. So this is going to be 10 kilograms, for example, times our value for g, which is 10 meters per second squared. All right, so that force is 100 newtons. This force is how many newtons? The 5 kilogram? Y'all think just a second. What is 5 kilograms is equivalent to what force on the surface of the Earth? What is it? What force is that? 50, right. So I just multiply it times 10, right? M times G. So I have 100 newtons over here times the distance, which is 0.3 meters, plus 50 newtons times 0.7 meters. I converted those centimeters to meters in my head. All right. So sine of 5 is pretty small, but I have FD 0.1. I get this is 0.0087. This is 0.3 times 100 is 30 Newton meters, plus 50 times 0.7 is what? 35 Newton meters. Those are the torques due to the weight of the arm. Where are we? Right here, the weight of the arm and the weight of the dumbbell. Notice that this torque is smaller than this torque. Well, that doesn't make any sense because we said the arm is like twice the weight of the dumbbell. Why does it provide more torque? Or why does this provide less torque than this, the dumbbell? The arm causes more torque. The weight of the arm causes more torque than the dumbbell. But the arm's a lot bigger. It's like twice as big. If you're Arnold Schwarzenegger. What is that? Why is that? Why is the torque bigger for the dumbbell than it is for the arm? There are three things that affect torque: the force, the moment arm, and the angle. Not the angle, but the arm's longer, right? The dumbbell is out here at a big R, whereas the weight of the arm acts right here in the middle point of the R, in the arm. All right, so so the deltoid, this is in meters right here, is going to be 65 divided by 0.0087 inverse 65. Oh, that can't be right. 7,500 newtons. Now, the angle might be a little off, the distances might be a little off, but the point is that your deltoid exerts a huge force just to lift a little bitty dumbbell, a little 10-pound dumbbell. How much do I weigh in newtons? Do y'all know? I think I told y'all this. Did I tell you? How much does the typical person weigh in newtons? Well, a person's about 70 kilograms, right? Sort of a typical person. And so, of course, it's wide range. But 700 newtons, all right? So this is like 10 times my weight that your deltoid is exerting to lift just a little bitty dumbbell. That's remarkable, I think. Don't you think that's remarkable? Again, the number is not quite right. We're just sort of doing some order of magnitude estimates. But it still exerts a very large force because of that shallow angle. Oh, so I had Newton meters? That's clever. Good. So I had Newton meters here, but over here I had meters. And so they canceled out there and there. That's clever. That's very good. It's nice to, or it's good to sort of watch your units as you go along through a problem. All right. You guys don't have to do a calculation like this, but we've done some that you will have to do where the forces are, at 90 degrees. You don't need your calculator for that. But you do need to understand how that angle um, affects the torque. All right, let's see. Just a few more things. The erector spiny? Is that how you say it? Spine, thank you. Um, where am I? Sorry, I lost my notes on this. This is the muscle that helps you to stand up tall and straight, right? That helps you to do this motion as well. I think it attaches. Gosh, y'all might correct me. I'm sort of guessing. Where does it attach on your back? I don't know. Anybody know? Uh, it attaches to the spine only, and then where does it go? To the sacrum? Are you guessing? Would you think so? Is she right? Do y'all know? I think she's right. Okay. I'm sorry. I'm not an anatomy person, but this helps you to stand up straight and bend over. It's important when we're thinking about this to think about our balance and our center of mass. So we'll come back to that, but let's look at our center of mass. The center of mass is a point in a body where you can imagine that all of the mass is located. All right, so for example, if I have a meter stick, I can imagine that all of the mass of the meter stick is located at what point on the meter stick? Typically with a regular object like a meter stick, it's going to be at the midpoint. Like we talked about with the arm, that if the arm was all the same all the way throughout, that this part was the same mass as this part, then the center of mass would be right at the center, at the geometric center. And so for a meter stick, the center of mass is at what position? This is 100 centimeters long. It's at a position of what? 50, right? So I can also change the meter stick. I can put a mass onto the end of it, and that will change where the center of mass is. So if this is 50, this is 0, this is 100, is it at 50, less than 50, or more than 50? More than 50, yeah. So the center of mass, actually it's at about 55. Okay, because I've added this extra mass here. Do y'all know where your center of mass is, roughly? Yeah, it's right about your belly button, right in your core. So you can imagine that when we're looking at problems, that you can imagine that all the force of your body is, all the weight of your body is at roughly your belly button. We'll talk about that more later as we get into rotation. Um, so where would the center of mass be for each of these objects? Right, the triangle, for example, where would the center of mass be? Would it be more towards the top or the bottom? Left, right, or center? Right. So more towards the bottom and then the center. For the arrow, maybe the center of mass be roughly right here. Listen, there are some geometric ways to actually calculate the center of mass, even for a human body. But we're not going to get into that. But you might see some diagrams of shapes, and I ask you where the center of mass is. And I'll give you several dots. I think I have an example problem soon. Arrow, uh, top, middle, or bottom. It'll be in the middle. It's symmetrical about that axis. Right, middle, or left. It's going to be more towards the right and along the center line. Right, so my center of mass here will be roughly right here. Think about that object, and I'll be right back. I need to grab something out of my office. where's the center of mass for this red semicircle? Is it towards the top or the bottom, left, right? Where is it? Just sort of yell out. I'm going to go across it. Yell out when I get to it. Right here? Right here? You think so? No, you're wrong. Look, this is a very similar thing. You ever seen one of these? This is a little bird. It's a little balancing bird. I'll pass it around so you can try it. But look at this. This thing is cool. Like, it's very stable. Like, I can do all sorts of things with it, and it won't fall off. Now look at it. Isn't that wild? I know. You can make one. Okay, you just sort of take like a couple of spoons, and I'll try to bring one next time, and I'll show you. But look, this is a lot like this thing. It actually has little weights inside of here. I'm gonna pass it around. Easy. I have another one. This one's a little lopsided, I think, or maybe that's the one that's lopsided. The World Wide Web. All right. Seriously. But you can make one. I'll bring a couple forks next time if I remember. Let me make a note. So I meant to bring it today, but I was in Bossier City yesterday. We had a meeting in Bossier City. 5 hours to drive up there for a 3-hour meeting and then 5 hours to drive back. And did you know that people live up in Bossier City? Like, I didn't think people lived that far north, but they do. Well, there are a lot of people up there. Uh, okay, so the reason that those things are so stable, the little birds, is because you're holding the tip of the bird right here, but the center of mass of the bird is actually below your finger. So in that case, and as with the semicircle, the center of mass is actually outside of the object. So the center of mass doesn't have to be in the object, right? The center of mass in this case is actually right about here. That's why it's very difficult. Some of you might be able to do this. But if you put, your butt, pardon me, if you put it all the way up against the wall and then you try to bend over, it's hard to keep your balance. I know that some of you are probably more flexible than I am, but it's very difficult to keep your balance. All right? Let's see if I can get this right. If I can, we'll do it. Um, I want you, yeah, so you can move over to the wall. So you'll just, everybody get up. Well, hold on. Keep your seats for just a second. But you're going to move over to the wall. When I'm standing right here, my center of mass is right over my feet. But if I lift my leg up, then my center of mass moves to a position that's outside of my body. And so I want you to try moving over to this wall or the back wall, because you have to be really flush up against the wall, and then lift your leg. You see how easy that is? Lift your leg without hanging on to anything, and very flush up against the wall. And this foot also needs to be up next to the wall. All right, y'all try that. You have to be the back wall or the side wall. Your your foot that's near the wall has to be touching the wall. Okay. All right. All right. Go with me. Let's see it. All right. So you're gonna be right up next to the wall with your foot touching the wall, and then you just lift your leg up. Don't leave the wall. You have to stay on the wall. See, if you can't do this, you're going to fail the class. I'm serious. Chelsea, come on, let's see it. Your foot's not touching the wall. Right. Foot against the wall. I feel like a drill sergeant. What are you, a bunch of babies? You can do this. Right, can anybody do it? I don't think so. You? What? No, you can't. All right, when you lift your leg, right, if I do it, if I lift my leg, I automatically lean over to move my center of mass from right here to over my foot. So, was anybody able to do it? The wall's not broken. Oh, yeah, you can do it. Is that what you're saying? Yeah, you need to move to a flat wall. All right, y'all can get back in your seats. All right, I want to show you something else. Oh, so in order to be well balanced, a person's center of mass should be over their feet. And so, some ways that a person can be off balance is they can just be holding like a large object in front of them, or they can have like a leg that's kicked up off to the side like that. Um, and I can push them. But anytime that you have your mass, not your center of mass, not over your feet, then you're going to be off balance. All right. Oh, you can bend over like I had before. I get that. Oh, very short arms, those people, don't they? Like they have no elbows or something. All right. Um, Something else I wanted to tell you all about that. Oh, so you can do this at home, and your friends will be amazed. I'm gonna do it with a meter stick, but you can do this like with an umbrella or a broom. A broom is really cool. Watch. I have this balanced on both my fingers, right? Watch as I move closer. I'm not making them stop or go. They just sort of go as they will. It's always going to stop at the center of mass. It has to do with the frictional forces and the normal forces, and they sort of change as you move your fingers from the middle, from the outside to the middle, but it's always going to stop at the center of mass. You can do that with any type of object, but in this one, it's always going to stop at 50 centimeters. Now, if I put something like a mass here on the end, I know that my center of mass is left, center, or right now, as you're looking at it. My left, you're right, right? So I'm going to move this here. It'll always stop at the center of mass. And I can put another one on here, and a similar thing will happen. But I want y'all to do it. So I have 1, 2, 3, 4, 5, 6, 7 meter sticks. Y'all come on up. You can grab a meter stick and just do this. You'll be in like groups of 3 or so. Not everybody at once. I mean, yes, everybody at once. There you go, Zach. Now just try that. You can try moving the little weights around too. But just sort of try that, moving your hands back and forth. Oh, you can see how the friction changes, the normal force. All right. Y'all can use, yeah, you can use that one. Here's one too. It has lead on the end if you want to use it instead. Daisy, don't chew on the lead, okay? It won't hurt you otherwise, but don't chew on it. One more thing, and then we'll do a few little practice questions before we move on to the next chapter. This isn't in your book, I'm pretty sure, but I show you this because we can sometimes take physical models. And there's this model that relates our walking speed. You don't need to know what the model is. I just really want to show you that sometimes we can take data and compare it to models. And we did this in the 151 class last year. I don't think we're going to do it, but maybe we will one day. But there's a model that describes your walking speed with regards to your stride. You know, what is your stride that you take? Your sort of natural stride. Everybody has a natural stride. And then also the leg length. Now, your stride and your leg length are somewhat related. But there are several models based on what is your optimal walking speed. And these physicists have found that it's related to uh, the stride length divided by the square root of your leg length. And so we did this in the class where we actually figured out our walking speed in meters per second, and then we divided this, or we plotted it up against stride divided by leg length. Now, this says that this should be a linear relationship, so that when we plot the data, that we get a straight line, and it actually is a pretty good straight line. Looks something like that. There's a lot of scatter because that's what happens, but probably at the end of the semester we'll try this out. We usually have our last class over at the rec center. We go and we lift weights, and we go to the studio room, and we do stuff in the classroom, and we might do this on the walking track this year, okay? So the point of this is that you can create these physical models, and they base this model treating your leg as a pendulum. A pendulum is like in a grandfather clock. And they said, well, there is some natural speed for a pendulum. And that's how I came up with this relationship between walking speed and these things related to your stride length and your leg length. So we can compare data to a model, and you know, the model might not be completely correct, but at least it predicts what the data that we see. We'll try that later in the semester, like I said, at the end of the semester when we go to the rec center. All right, let's try some of these. Just sort of one last hoorah before we move to the next chapter. Again, if you're not registered, just go ahead and use your clicker. We're going to do this one first. I'll zoom in a little bit. If you finish, go on to the others. We'll go to the one below it after this. Block has two ropes. Person pulls to the left, person pulls to the right. What is the net force? All right, I'm going to stop at 50. Cool. Any more time? 55, I'm stopping. With the clicker questions, if you get them wrong, it's not a big deal. I say just keep coming to class, keep doing them, you'll be good to go. All right. D, is that D? I think that's right. Yeah, that's right. So remember, whenever we do net force, I think we have a question on the quiz like this. If I have 20 newtons in this direction and 10 newtons in this direction, then I have a net force of 20 minus 10. That's equal to 10 newtons. So the net force on this thing is 10 newtons to the right. So if I were to draw the net force vector, you know, it would be like this, 10 newtons to the right. What would be the acceleration of that object? Do you have any idea? How quickly would its speed change? Well, it has a net force, F, of 10 newtons. Newton's second law is what? You know, tell me Newton's second law in equation form. All right, F equals ma. So Newton's second law says F equals ma. So A is equal to F divided by m. My net force, Newton's second law refers to our net force. In this case, our net force is 10 newtons divided by the mass is 10 kilograms. So it's going to be 1 meter per second squared. That force, that net force of 10 newtons, is going to cause an acceleration of this 10 kilogram block of 1 meter per second squared. All right? You can see test problems like this on the test coming up. It's not next week, I don't think, is it? It is next week? Oh my goodness. What day? Tuesday or Thursday? Oh, what's today? Thursday? All right, the force due to the muscles in this figure produce what kind of torque? These are your erector spinae. This force right here, as I said, attached to your spine and your sacrum. Um, the spine, is that your insertion or origin when it's connected at the spine? Are you serious? But it moves. Oh, at the sacrum? The sacrum would be your origin. Right, uh-huh. At your spine, when it's connected to your spine. To your sacrum? Okay. Never mind. Just let's rewind about 30 seconds, okay, and just forget I said that. All right, so anyway, what is the the torque that's caused here? Is it a clockwise torque, a counterclockwise torque, or no torque at all? All right, let's stop um, at 128. 128. Okay, this is a clockwise torque because it's going to cause this thing to move in this direction. And that direction is like a clock moves. It's clockwise. All right. This figure shows a wedge of wood. Which arrow refers to its center of gravity? A, B, C, or D? I got a good joke for y'all. Yeah, Zach. Well, it doesn't really matter where it's laying. It can be oriented any which way. The center of mass of an object doesn't change unless the object changes. Which is closest to the center of gravity? A, B, C, or D? All right, we'll stop at 35, 35. Awesome. C is right. Um, what do you call a boomerang that doesn't work? A stick. All right, let's try this next one. Muscles are connected to the bones at least 2 points. The point attached to the bone that moves is called the what? All right, I'll stop at 23. 23. Okay, D is right. The erector spinae. Help us to do which of these? All right, I'll stop at 25. Okay, awesome. B is right. Uh, what do you call a lady with one leg? Or what is the name of a lady with one leg? Eileen. Sorry. I'm glad that all of you have two legs because one day I'm gonna get one of your legs. I might be able to use any of my jokes. All right. Friction is a force that which of these? All right, I'll stop at 30. Okay, it opposes the direction of motion. Friction always opposes, well, it almost always opposes the direction of motion. There's some very special cases where it might actually go in the same direction as the motion, but almost always opposes the direction of motion. And then 50-pound child at the end of the seesaw, 2 meters from the fulcrum, where must a 100-pound child sit? All right, and I'll stop at 35-ish. Guess if you're not sure, ask your neighbor if you like. I'll go on to 40. Stopping at 40. Okay, that was good. C is right. Good job. Um, so on my seesaw, it's balanced at the center. The 50-pound child sits over here. 50 pounds at 1 meter. That gives me 50 meter pounds. That's not really a unit, but we'll call it that. 50 meter pounds. And then on the other side, I have the bigger kid at 100 pounds. Times the distance, which is this R value, and you solve that 50 divided by 100 is, or excuse me, no, that should be 2 meters. Yeah, this should be 2 meters. Uh, I'm sorry, this should be 100 meter pounds. All right, 50 times 2 is 100 to give me this torque, and then I divide by 100, so R is equal to 1. All right, you'll see those sorts of torque problems. The math will be fairly simple, but I want you to know how to figure out what is the balance of torques. And then you might also see, like we did in class, some problems where you have two forces on one side and one force on the other. And then you might also see some class, this is a class what lever? It was a class 1, but you might see a class 2 or a 3 lever as well. All right, clear on chapter 1, sort of where you are. As you prepare for the exam, what I would do is read through the chapter, go through the notes. Remember, chapter 0 isn't in the book, but that will be on the exam. That wasn't on the quiz, but it will be on the exam. The dimensional analysis, the units, the standards, those sorts of things. I would also go back to the old exams on the website, the course website, which is linked from Moodle. There are some old exams. There are also some in the back of your workbook, but you can look at the old exams on Moodle, on the course website, which is linked from Moodle, and just practice those. I'd print them out and don't look at the answers. Just run through them and see how you do. And if you're shooting 100% on all of them, you 0, 1, and however far we get through 2. I'll let you know where the material stops. My exams are sequential as I lay them out to you. So when you open up the exam, the first questions will be about chapter 0. The next set of questions will be about chapter 1, and then the next set of questions will be about chapter 2. I suspect that we will get through the physics portion of chapter 2. But we'll get where we get. I don't have. All right. Chapter 2, pretty good chapter. It's on fluids and pressure, and it also deals a lot with sort of, how we move fluids through our body. We'll talk about the eye, um, the, the bladder, lungs, all sorts of how we deal with fluids in the body. But first, we're just going to define pressure. Pressure is defined as force, or excuse me, a force per unit area. and it is pressure is required to move a fluid. So anytime I have a fluid that moves, it's because you have a high pressure and a low pressure, and it's going to move from the high pressure to the low pressure. So we can think of pressure as sort of forces for fluids. In fact, it is. It's a force per unit area. But it's required to move a fluid either in your body or around your body or just in nature. So, for example, in the body, it comes up a lot. Breathing. We'll talk about how when you breathe that you have high and low pressures, um, blood flow. In the second part of this chapter, you'll need to know the chambers of the heart and how blood flows through the body, stuff that you probably already know, many of you. Blood flow, digestion, delivering medicine, etc. Digestion. The mathematical definition, I've sort of written it in words, but pressure is equal to force divided by area. Just to remind you about your area, area is equal to length times width. In general, like if I have a rectangle or a square or whatever, if I'm dealing with a circle, it's equal to pi r squared, or roughly 3 times the radius squared. Pi is roughly equal to 3. We'll just sort of take it as a 3. Although I don't think very few places where you have to actually calculate the area. All right, the units of pressure, gosh, there's actually lots of different units for pressure. Um, basic units that we'll use are called pascals. That's equal to, or it's abbreviated rather, as PA, and that's equal to 1 Newton per square meter. We're going to get into some units that have sort of more basic units. That is, the Pascal we use to describe pressure, but it's also newtons per square meter. Sometimes you might encounter questions like that on the test where I ask you, what are the base SI units of pressure? And an option might be newtons per square meter, though a newton isn't a base SI unit. It would all be in terms of mass, length, and time. But if you have questions about that, you can just go back to the original formula and say, well, F is in newtons, A is in square meters, so a Pascal is a newton per square meter. We have other units. You're probably familiar with many of these, and we'll see them at various times. We can have inches of mercury. You can have millimeters of mercury. Atmospheres. This is sometimes ATM. Bar, or rather a bar. This is equal to, what's it equal to? 100,000 pascals. Centimeters of water. We'll talk about what these mean. These are all very similar, especially the inches of mercury, the millimeters of mercury, the centimeters of water. You ever measured blood pressure before? Yeah, what do you see when you, like you're in the hospital, and what do you see when they're measuring the blood pressure? What's the little thing that goes up? Silver thing. That's mercury. There's a little tube of mercury, and as the pressure increases, that little tube of mercury increases in height. And we'll see where that comes from, that it's actually measuring the actual height of the column of mercury. We'll calculate how that comes about. All right, there are 3 possible sources of pressure in a fluid. Your book talks about this. Where is it? Oh, weight of the fluid. We'll go into each of these separately. Weight of the fluid. That means that if you're at some depth in a fluid, then you feel the weight of the fluid bearing down on you. You ever been in the swimming pool going down to the bottom? Right? You feel the pressure pushing on your body. And in fact, you have a very immense pressure pushing on you because you're sitting inside of a fluid right now. Did you know that? That you're sitting inside of a fluid? Because fluids include not only liquids, but it's anything that flows. So it includes liquids but gases. Were y'all worried? You think you're going to drown? Because I told you were sitting in a fluid? All right, weight of the fluid. Um, what was my second one? Oh, an external force applied to the fluid. So, like for example, I don't know if any of you ladies are mothers, but if you are, you know that well, probably not. But if you were, you would know that when you were pregnant, that the baby sometimes pushes on your bladder, and that force increases the pressure of the fluid inside the bladder. So next, I've never been pregnant either, but I've heard about it. My wife has been pregnant. All right, and then also an internal force due to the interaction of molecules. And we'll talk about that ideal gas law kind of stuff, where if I increase the temperature of a material, of a gas, or even of a fluid, it can increase the pressure because those molecules start moving around more and it increases the pressure. The internal force due to the interaction of molecules. There's probably a good middle school joke too there that has to do with, gas or whatever, but I'm not going to go there. I'm sure if my son was here, he could do that. Okay, so let's look at these. The weight of the fluid. Uh, this is, we're talking mainly about like atmospheric pressure, but atmospheric pressure results from the weight of a fluid at sea level. And to derive this pressure, we consider a column of fluid over a particular point. I'm going to show you the derivation because it's not that complicated, but you're not responsible to know the derivation, but you do need to know how pressure and depth are related. So let's imagine that I have some fluid, and there's some point down inside the fluid, say it's a cube, like that, all right? I can imagine that that cube has a column of liquid just sitting on top of it. And it does, in fact. Like it has a column of liquid that sits right on top of that cube. Now, the weight or the area of this cube is equal to A, right? The face of that cube is equal to A. The liquid here has a density rho. Now, just to remind you, you should have had this, but I think you probably know this, but density is equal to a mass per unit volume, right? All materials we describe by their density. Some are more dense than others, like wood, for example, is less dense than, say, water, and that's why it floats, and we'll see that later. But liquid has a density rho, and so I can write the mass of the liquid, or the mass of the fluid, is equal to m times g, which is equal to, if I solve for m, I cross multiply, is equal to rho times v times g. So rho is the density of the fluid, v is the volume of the fluid that goes over here. So there's this column of liquid that comes up that has a volume of fluid, v, and then g is the acceleration due to gravity from Newton's second law. This has a volume equal to v. Now, if I want to know the pressure, I'm sorry, this is the weight of the fluid, um, the force weight of the fluid. The pressure then is equal to that force divided by the area, So it's going to be rho times V times G divided by the area. You with me, sort of, kind of? All right, let me step back through it. But if you don't get the derivation, that's okay. But I do want you to understand that this pressure does arise from having a column of liquid that sits down on top of the point in space. All right, and if you get that, and that's okay. And then we'll get to the actual equation in just a second. So I have this imaginary box inside this liquid. There is a column of liquid that sits on top of it. We're talking about an actual liquid here, but it works for gases too. There's a column of liquid here. This box has an area A. That's important because my pressure is equal to F over A. Now I want to figure out what is the force that this column of liquid is imparting upon this imaginary box. The force is equal to the mass times the acceleration due to gravity. The mass is equal to rho times V. That comes about from my definition of density. Rho is m over v, so m is rho times v. And then g I just carry over. So now I have rho vg divided by a. Then I can take an extra step because v is equal to the area times the height times g divided by the area. What that's saying is that if this is a column of liquid like that, it has a certain volume that's equal to the area divided by or multiplied times the height. In general, that's true for volume. If I multiply the cross-sectional area times the length of that object, I get its volume. Like a cylinder is pi r squared times the length. Pi r squared is the area of a circle, and I multiply it by the length. All right? So I get my final expression for pressure. P is equal to rho GH. And that's really the important part. I do want you to understand that this pressure is due to this column of liquid that sits on top of you. So for example, all of you, you have a column of a fluid that sits on top of you. The Earth's atmosphere extends, you know, many thousands of feet up above the surface of the Earth. And all of that gas, it doesn't seem very heavy, but all that gas sits on top of you and pushes down on your body. Now, we don't really experience this because we have forces pushing in all direction, and plus our bodies are mostly water. They just don't compress very easily. But we still have this very immense pressure pushing onto us due to this column of fluid. As depth increases, the pressure increases. As depth increases, the pressure increases. That is to say that as H goes up, P also goes up. People are sometimes confused by my P's. I often put a little base on them. That's just to help you distinguish them from the Greek letter rho. So usually when I write the P, I just put a little base. If you don't want to do that, that's fine. Okay? But that's my P. You with me? But what you need to walk away with is that column of liquid or column of fluid exerts a pressure at a certain point. The weight of that fluid actually exerts a pressure, and that pressure is dependent upon the depth that you're in that fluid. Taylor? No, yeah, I give you an equation sheet, so you don't need any formula. I mean, you have everything that's, so no, you don't need to memorize anything, but you do need to know to use them when it's relevant. No, no, I'll give you very simple numbers. You know, G is 10, H is say 2 or whatever. Give you the density. It will be simple multiplication. Don't worry about the math. The math is not the hard part. Uh, yeah, of course. All right. All right. So atmospheric pressure is really, really big, but it's kind of difficult to imagine. because as I said, the net force is equal to 0. Atmospheric pressure, 1 atmosphere, watch out, I'm about to blow your mind. It's equal to 1 times 10 to the 5th pascals. That is, it's equal to 100,000 newtons per square meter. So, like these tiles on the floor are about 1 square meter. There's a total force of 100,000 newtons pushing on this tile of the floor. 100,000 newtons. Now, a person is about, 700 newtons. So you got a couple hundred people standing on top of this tile. The atmosphere that goes up pushes down with 100,000 newtons per square meter. There are a couple of ways that we can observe this. A barometer. Are we going to get to a barometer? I forget. Anybody read chapter 2 yet? Yeah. You should be reading chapter 2. I don't think. Yeah. All right. So a barometer. Barometer works like this. Barometer, you have a tube that's open on both sides. Sometimes you can have it. Actually, a barometer is closed on one side, but we're going to just imagine that it's open on both sides. You put a fluid in it. You measure. This is what your blood pressure is doing. You measure this length, h, your blood pressure monitor. You measure this height, h, and that tells you the pressure. So imagine that I have one force pushing in over here, and then I have another force pushing in over here. These are not the same. Like if I call this one F1 and F2, which of those forces do you think is bigger? Is it F1 or F2? Which is the bigger of the two forces? Think about it for just a sec. Which force is bigger, F1 or F2? Let's just do it as a clicker, actually. Which force is bigger? We'll do A for F1 and B for F2. Which of those two forces is bigger? All right, we'll stop at 25. Oh, you're awesome. You're awesome. What lies at the bottom of the ocean and twitches? A nervous wreck. Okay, so here our F1 is bigger. It's like you can imagine that it's pushing this fluid down and pushing it up into here. So I can calculate now what is that pressure that's being caused by that force F1. And that pressure is equal to rho times G times H. Whatever the density of this material is, times the acceleration due to gravity, times H. So when you measure your blood pressure, that's what it does. It measures the height of that column, and that gives you a direct measurement of your blood pressure. Likewise with a barometer. You measure the height of the column, and that gives you a direct measure of the pressure. I'm going to show you a little video. Pause it also. You ever used a straw before? Have you? No. What's that? It was just newspaper, right. And so what holds it down is the actual atmospheric pressure. Usually, right, we're moving around and we feel net force of 0 due to atmospheric pressure because, I have one force in this direction and one force in that direction, so they all cancel out. But when you lay a newspaper out flat on the table, you have the pressure pushing down, but you have no atmosphere pushing up. And so it holds it in place, allowing you to do this thing with the ruler or the pencil. It's tricky because the newspaper has to be really flat. And that's why it's difficult to do. And Jason did a good job, I think. Don't you think Jason did a good job? Yeah. Huh? He wanted to talk. I could see, like, and the music was going. It was awesome. All right, so a straw works something like this. But you didn't know this. So you have a liquid, you have a straw, and inside the liquid, you have some pressure that's pushing in here. That's the atmospheric pressure. And then you have, this is the guy, I can never do this right. It's a very large straw or something. You try drawing a guy drinking from a straw. It's not easy. So, um, what happens when you use a straw is that it's not, we always think of it as like, oh, you're sucking up the stuff into the straw, the fluid into the straw. That's really not what's happening at all. What's happening here is that you create a low pressure inside of your mouth, and you have a higher pressure outside of your mouth that's pushing down on the liquid, and that high pressure will actually push the liquid down and push it up into the straw and into your mouth where, you drink it. Right? It doesn't have, it has a little bit to do with sort of what you do inside your mouth, but really it's just that you're creating this low pressure. Because remember, in order for a fluid to flow, it has to move from a high to a low pressure, from a high to a low pressure. And that's what's happening here. You can do a thing where uh, you actually put two straws. I can try this with your friends if you like. I didn't have enough straws for us all to do it. But you have two straws. One's, they're both inside your mouth. One of them is in the liquid and the other is outside the liquid. And then you try to drink from that. Is it going to work? No, it doesn't work. Because then if you have one straw that's in your mouth, you can't create a low pressure inside your mouth because it's open up to the atmosphere. So you still have a high pressure inside your mouth, but you have a high pressure outside, so you don't get any fluid flow. You can try that at lunch if you like. All right, let's try these quick tests. We'll do the one on the left first. If you weigh 180 pounds and stand on one leg, what is the pressure on the knee joint? The knee joint, has roughly an area, contact area about zero point 0.5 square inches. Can y'all see that okay? Yep. All right. Let's stop at 50. 50. Okay, B is right. Pressure is force per unit area. Force over area. That's going to be 180 pounds divided by the area, which is zero point 0.5 square inches. 180 over zero point 0.5. I know that some of you think that's 90, but it's actually equal to 360. So 180 divided by a half is the same as 2 times 180. Right, and that's equal to 360. In physics, pressure is defined as which of these? All right, let's stop at 28. Oh, awesome. That was great. Well, the answer is right there, but it's still get a good joke. What did the janitor say when he jumped out of his supply closet? Supplies! Okay, I know y'all are tired. I know you're ready to go. We have 5 more minutes, though, okay? So we're going to push on. Let's look at pressure due to an external force. So remember, we're going through these. What are the possible sources of pressure in a fluid? And we said it's the weight of the fluid. It can also be an external force applied to the fluid. It's like the baby pushing on your bladder, causing you have to go pee. So Pascal's principle defines this. Pascal's principle says that when pressure is applied to a fluid in a closed container, that pressure is felt throughout the container. So for example, if I have a container that's filled with fluid, let's say I put a piston on it and I drive a force down with a certain pressure, so I have a force per unit area, that same pressure is going to be felt all throughout the fluid and pushes on all sides of the container. It's a good thing. That's what allows us to measure our blood pressure, right? We can measure what the heart is doing here, here, right? By just feeling of what it's doing over here. We consider that to be a closed container, and it's a little bit different, but it allows us to measure the pressure of the blood or measure the heart rate. So the heart applies pressure that is felt throughout the body. The baby pushes on its mother bladder, etc. We'll see also that this comes up in. Actually, do we see that? No. Let me also just address this. If you have a hydraulic lift, some of you use hydraulic lifts, it uses this idea of Pascal's principle. Hydraulic lift looks something like this. You have a small piston on one side and a big piston on the other. You fill it with fluid, usually hydraulic oil, but water will work just fine too. It has to be an incompressible fluid. I put in a small force over here, and I get out a big force over here because I have F small over A small is equal to a big F over a big area. Because I have this difference in the two areas, I get a difference in the forces. But the pressure, F over A, that I feel over here is also felt all throughout this container. All right. So if anytime you have a hydraulic lift of anything, you're lifting your car or lifting a patient or whatever, the hydraulic lift operates by Pascal's principle that the pressure is felt throughout. All right. Can I borrow somebody's book for just a second? No, you have your textbook, the little textbook. I know that y'all like me, but you're about to like me a lot more. Because we're going to have a quiz on Tuesday. And it's going to go, not the whole chapter on chapter 2. It's just going to go up through page 48. Okay, I'll send y'all an email. Do y'all like me more now? It's to help you for the test, okay? So just be prepared on Tuesday for a quiz up through page 48. I'm going to send you an email message about it, but up through page 48, up to applications of the human body, chapter 2. Don't go past applications of the human body. All right? Sorry, I know that my view in your mind just went down a little bit, but it's good for you. Most likely, yes. All right, y'all have a great day. I'll see you Tuesday. Remember, we'll have the quiz at the beginning, just about 10 minutes or so.